Digital trust once meant certificates and PKI. Not anymore. Today, it also includes ledgers, digital signatures, regulation, and quantum-safe choices. In this course, we'll connect PKI, KSI, blockchain, post-quantum cryptography, and eIDAS into one practical mental model. Here's the path we'll follow. We'll begin with PKI fundamentals, then place KSI and eIDAS in context. From there, we'll look at blockchain as a trust anchoring layer and compare the models. Finally, we'll address post-quantum risk and what it means to design a migration-ready trust architecture. The course moves from what most systems rely on today to what they must handle tomorrow. PKI comes first because certificates, identities, TLS, signatures, and code signing form the foundation of modern digital trust. Then we expand into KSI and eIDAS, where trust becomes evidence, timestamping, legal recognition, and regulated services. Blockchain anchoring gives us a decentralized audit option, but not a universal answer. Finally, post-quantum cryptography raises the long-term question: will this architecture still be trustworthy when the cryptography changes? Use this course based on where you are starting. If you are new, move sequentially and give the PKI foundations real attention. They support almost everything that follows. If you already know the basics, focus on comparisons: what each technology solves, where it overlaps, and where its boundaries are. If you are advanced, treat the material as a reference for architecture, compliance, and migration decisions. Whatever your level, learn actively. Sketch trust chains, note assumptions, compare threat models, pause on overloaded terms, and discuss questions with others. Plan focused review time. Now we move from orientation into the first building block of digital trust, PKI. We'll look at how certificates connect identities to public keys, how certificate authorities create trust chains, and how validation, signatures, and revocation checks work together to make trust verifiable. PKI exists because the internet is full of strangers. When your browser connects to a server, it needs quick answers. Who is this? Has anything been altered? And should I trust it? A certificate is like a digital passport. A certificate authority is the issuing government. Validation is the border check that decides whether the credential is legitimate. That same model supports TLS websites, signed email, code signing, device identity, documents, and enterprise login. PKI gives us the technical framework for trust, but policies and operations determine how reliable that trust really is. At the core of PKI is an asymmetric key pair, two mathematically linked keys with different roles. The private key must stay secret because it proves control. It can create a digital signature, and the matching public key lets others verify that signature. In encryption workflows, data can be protected with one key and recovered only with the corresponding key, depending on the protocol. The public key is meant to be shared, but in PKI it becomes trustworthy only when a certificate binds it to an identity. If the private key is lost or exposed, that trust breaks. An X509 certificate is an identity card for a public key. It says, "This public key belongs to www.example.com" and includes supporting details: who issued it, when it is valid, its serial number, and what the key is allowed to do, such as TLS server authentication. The critical part is the issuer's digital signature. That signature protects the certificate contents from tampering and lets a system verify who vouched for it. Still, the certificate is not automatically trusted. Trust comes from validating the signature, the issuer, the dates, and the CA chain. A certificate authority is the trusted issuer in a PKI system. An applicant requests a certificate, but the CA should not simply hand one out. It first validates the applicant's identity against published policies. If validation succeeds, the CA creates the certificate and signs it with the CA's private key. Later, a browser, application, or user accepts that certificate because it trusts the issuing CA or a chain that leads back to it. That trust only holds if the CA is well governed, audited, legally aligned, and rigorous about protecting its signing keys. A certificate chain is delegated trust. The root CA is the trust anchor your system already accepts, so its private key is treated like a crown jewel, often kept offline and protected by strict controls. Rather than signing everyday certificates directly, the root signs an intermediate CA. That intermediate then signs certificates for websites, users, devices, or services. During validation, the relying party works back upward. End entity certificate, intermediate, trusted root. If every signature checks out and the root is trusted, the identity can be trusted. When a browser or service receives a certificate, it does not accept it on site. It runs a validation path. First, it parses the certificate and checks the dates. Then it confirms that the name matches the site or service being reached. Next, it builds a chain from the presented certificate through any intermediates to a root certificate in its trust store. After that, it checks usage, policy, and revocation status. Only if every required check succeeds does the relying party trust the certificate. If one fails, it rejects it. Digital signatures start with a practical shortcut. Do not sign the whole document directly. Sign its fingerprint. The signer hashes the data, then uses the private key to sign that hash. The verifier hashes the received data again, uses the signer's public key to check the signature, and compares the results. If they match, the data was not changed, and the signer had access to the private key. PKI adds one more requirement: trust the key. The certificate, issuer chain, expiration, and revocation status must also validate. Revocation answers a simple question. What if a certificate was valid yesterday, but should not be trusted today? A KRL handles this by distributing a signed list of revoked serial numbers. It works well at scale and preserves privacy, but freshness depends on how often clients fetch updates. PQC asks about one certificate at a time, which can give a fresher answer, but it adds latency, depends on a reachable responder, and can reveal browsing or connection patterns. Revocation is essential, but reliability and client behavior make it harder than it first appears. One key PKI lesson is that failures rarely come from broken cryptography. They usually come from operations, unprotected private keys, unnoticed certificate expirations, poor inventories, weak revocation, excessive CA authority, and audit gaps. Each certificate needs lifecycle discipline. Someone must request it, validate the identity, issue it correctly, deploy it safely, monitor it, renew it before outage, revoke it when trust changes, and retire it cleanly. Treat the risk list as a control map, not just a warning. This matters because eIDAS, blockchain anchoring, and post-quantum migration all assume the PKI foundation can be governed, measured, and changed without losing trust. To wrap up, PKI gives us a practical trust model. Certificates bind identities to public keys. Trust chains connect those certificates back to trusted roots, and signatures prove authenticity and integrity when validation succeeds. Real security also depends on revocation, lifecycle control, and CA governance. Next, we'll use this foundation to explore KSI and the eIDAS context.